Okay, so the agenda for today is first I'll start with IP over IP as ULP, what it is and how we use it. What would be the gains and what would be the goals of having it accelerated. Some basic slide about the architecture for accelerating it. Why do we want a vendor-specific acceleration, which will be proposed here? What would be the packet flows for the accelerated and non-accelerated modes? Following discussions on the mailing list and contributions made by Intel and also proposed earlier today, we have an initial proposal, and now we updated the proposal to merge with the Intel patches, so I'll show the current proposal. Also, I'll show what the ULP, IP over IP ULP will remain handling, what event handling will be remained in the ULP. A quick performance update that we saw, and a summary. Okay, so how the stack looks today. So on the right, we can see the layers that represent the ULP. So on the bottom here, we have the network interface. The network interface is capable of doing stateless offload for IP over IP traffic. So the same as it does for Ethernet, it can also detect and intercept IP over IP frames. It is familiar with the headers and is capable to do the offloads. And the challenge is how to enable that. So the usual stack, we have the Infiniband provider. In our case, it's MLX IB. We have the generic IB core and the IB device that represents the kernel verbs. Then we have the generic IP over IP ULP driver that is written on top of the verbs API and basically registers the OS network device interface, the NetDev. On top of that, we have the usual TCP/IP stack and the socket layer, and then, of course, the application. So IP over IP is basically encapsulation of IP packet over Infiniband headers. As I mentioned, today the implementation upstream is as ULP. It uses the kernel API, the kernel verbs, as the underlying API. There are two modes that are supported today. The unconnected, based on UDQP service type, and the connected, based on reliable connection QP service type. So essentially, today with RC, the device is capable of exposing a larger MTU, and using that, it's doing something similar as LSO, large send offload, where in LSO case, the hardware is the one that breaks the packet into smaller MSS size packets, but we expose a smaller MTU. It's not so popular, the connected mode, and we'll see our plan for it in the next slide. The ULP uses RDMA services as the subnet agent, the communication manager in case of RC, and MAD services. Today, the ULP is capable of performing checksum and large send offload in terms of stateless offload support. And of course, we would like to add many more, and any new feature, if we go with by the book and by the way it is coded today, every such feature needs to be exposed through the verbs, kernel verbs API initially, and only then it can be added to the IP over IP ULP. Also, another challenge is how we present management tools and how we allow the standard management tool, ETH tool, to also be applicable for the IP over IP. And also for doing so, since the underlying interface of the ULP is the kernel verbs, it mandates also adding callbacks or services for servicing ETH tool, if we want to allow that. Okay, so accelerating IP over IP, what are the goals, what the targets that we put into mind? So first, we would like to allow the stateless offloads, the large receive offload, where we do desegmentation of TCP in hardware, the accelerated RFS, that is a unique feature where you can assign flows to cores. Of course, receive side scaling and also transmit side scaling, the multi-queue stuff for send and receive. Also interrupt moderation, where we can perform also active moderation updates in terms of changing the period or the interrupt rate. In future, we also would like to add tunneling offload. We'll talk about that in the next few slides. Also, in terms of supporting multiple partitions, today the ULP requires, there's a kind of an add child mechanism where we instantiate a new instance of the ULP to serve a new partition, a new PKI, which is very different with what we do with Ethernet. With Ethernet, if we want to support multiple VLANs, we can use the same hardware resources, but only push a different VLAN through SKBuf metadata to the net device. So we would like to enjoy the same, to enable at least the same model with IP over IP, where we can share resources across multiple PKIs. Also, we would like to allow vendor-specific optimizations if there are some send or receive optimizations. For instance, in our case, we have a multi-packet descriptor, so we can allow sending multiple packets with a single descriptor, very efficient for small packets, so we would like to allow that as well. In terms of management, as I mentioned earlier, we would like also to allow ETH tool to manage IP over IP. So we need the ETH tool, the famous ETH tool ops calls support. Also, a target is not to bloat the KAPI. If we would like to add callbacks or function calls for each and every one of those features to the kernel verbs, it will be pretty much bloating the kernel API. Also, we would like to use joined code. So we would like to use the vendor-agnostic IP over IP ULP code that is upstream and very mature. We would like to reuse the code there as much as possible, mainly for the control path. The goal is to allow the enhancement for UD IP over IP mode. We don't see much future for the connected mode. There are serious scalability issues with the connected mode. And also a very important goal, as I mentioned, to use the generic ULP code. This ULP will remain upstream, will use vendor enhancement if they are there. If they are not there, it will revert to the legacy path of sending and receiving all the data path over the kernel verbs. So the same ULP supports non-accelerated providers as well. Okay, the architecture for, or the changes in IP over IP architecture for supporting this is that, as I described, we separate the control and data paths. In terms of management, what we would like to leave for the IP over IP, for the ULP, is the interface registration. There's a lot going on with multicast management. I elaborate on the next slide. Also, event processing. There's some event processing being done towards the Infiniband subnet manager events, if it's a local lead change, if it's a SM lead change, for example. Also handling the link state, if there are changes in the link state or link speed. Also path resolution and path cache management. Whenever the IPOIB needs to send a packet to a peer, a remote node, it has to perform some path calculation and also store some path cache so we don't overwhelm the SM with path queries. Also handling the address resolution and the IBRP. In terms of data path, we would like to have the multi-queue support for RSS and TSS, manage the buffering so we can handle that in an optimized way. Of course, receive and send frames. Why do we see the solution to be a vendor driver or vendor code for data path? So as I said, allow hardware-specific optimization, no longer bound by verbs, kernel verbs API, which should be and remain generic. Also, hardware-agnostic APIs requires some hardware-agnostic structures. So as we know, the verbs has large structures for managing work requests and completions. So we would like to use much more compact structures for data path. Also, if we would like to have a hardware agnostic API, mostly we need to tailor callbacks and hardware function pointers for each vendor. So we would like to avoid dereferencing functions in data path as much as possible. In terms of parameter sizes, I mentioned the issue with the work request and the work completion. And also use only necessary data for the data path. It's very important also for cache line optimizations and cache misses if we use very generic and large structures. Also, in terms of the instruction cache, we would like to have in data path very optimized code. So we are very optimized in terms of the cache. And also, we would like, another point is to enjoy compile time code optimizations. If we keep using function pointers, we basically block the compiler from doing its work in optimizing a function that includes the all code inside. Okay, in terms of packet flows, so in transmit, the ULP, if we look at the portion, what the ULP should do and what should be optimized. So in terms of send, we will keep the IBRP handling and the resolution, the address resolution in the ULP code. Also, following the IBRP, there's the path query. We would like to leave that for the ULP. In terms of the send itself, then we would like to use the send in a specific vendor driver. The vendor driver will be parsing or building the hardware work queue element directly from the TCP/IP stack descriptor directly, which is the skbuf. So we have skbuf to hardware work request element directly instead of having, as today, skbuf being parsed and translated to the IBV send work request, and later on the IBV send work request is being parsed and used to build the hardware work request element. And of course, doing the send operation and ringing the send doorbell. Also on the send path, the transmit completion processing, we would like to see that in the vendor driver as well, so we don't translate the hardware completion to IBV work completion and only then parse it. And finalize with the free SKB of the sent data. On terms of the receive path, so the vendor driver would be the one that will do the completion queue entry processing of the hardware. No need to copy to the IBV work completion. in terms of the work queue and the receive work queue processing. So also the vendor driver will be doing that. We'll be servicing the NAPI and POL calls and the receive SKB. And of course, allocation of the new receive buffer and posting it to the hardware. In terms of multicast flow, I mentioned earlier that we would like to keep that in the ULP. And to explain what it is, so in terms of IP over IB, the IP over IB, when it comes up, it joins what is called the IP over IB multicast group. It's a well-known multicast MGID that is used basically to broadcast on a specific partition to allow broadcast services for IP over IB, and mainly IB ARP requests are being sent on that broadcast MGID. Another role of joining that multicast GID is that in the reply there are some basic parameters the IP over IB needs in order to operate. One of them is the Q key, which is used whenever we create the IP over IB QP. On send, when a multicast packet is being sent, unlike Ethernet, in the IB case, still there is work to do towards the subnet manager and towards the switches. So the IP over IB catches this multicast packet send and performs a multicast join operation towards the subnet manager with a send-only member attributes. It mentions the same that it's a sender only on that specific multicast group. And following, it attaches the local IP over IB QP to that MGID and MLEAD that is returned by the subnet manager. And the leave operation is being done according to an aging scheme. Whenever there's a multicast receive request that is being issued locally because there's some application that is listening to a multicast group, the TCP/IP stack and the Linux stack will update the net device multicast list. We trap that update and according to that send also a multicast join to the subnet manager, this time as a full member because this time we would like to receive. And whenever there's an undo to that call, if the multicast membership is being revoked, of course we send the leave. And another role that the IP over IB ULP is doing here is also make sure that joins and leaves are being sent once per port. So if we have multiple applications listening to the same multicast group, only when the last one retires or leaves, we send the leave to the SM. Okay, so how we propose to allow the ULP acceleration? So the initial proposal was to extend the kernel verbs to allow a single query to a structure, which is called IP over IB operations. Those operations, as detailed here, include what is necessary for optimizing the data path. So we had to have some init and open and stop calls, so we can allocate or release the hardware-specific resources. There's the multicast handling that needs to be done because in the enhanced case, we manage the queues, we manage the underlying so-called QP of the IP over IB, and we need the send operation. So all of that was whatever we identified as callbacks that we need to have in order to expose the enhanced mode, we wrapped them in the what we called IP over IB ops, and with a single verbs addition to the kernel verb, we can extract this structure and those calls. Also, the plan was to add ethtool ops to this structure, so we can also serve ethtool and managing the IP over IB. Okay, so that was the initial proposal. Following Intel proposal and the talks on the mailing list, we would like to merge it to a single proposal. So instead of having the IPOIB ops structure with the specific enhanced calls, we will use the alloc RDMA netdev callback instead of the query IPOIB ops, which will return a netdev. And the netdev already includes all the NDOs necessaries for enhanced operation. So basically, the vendor driver can decide which NDOs it would like to implement itself and which one it will leave to the ULP. So the ULP will be calling alloc RDMA netdev and monitoring the netdev return value. And the RDMA net device that is pointed by the return netdev, we'll see in the next slide how. This RDMA net device will include whatever is necessary in order to manage the enhancement. And in our case, the additional function that we need is the multicast handling as specified here. In terms of the send operation, there is an issue of passing send information that is specific to IP/IP, to Infiniband, the address handle, in a separate function and not using the XMIT of the netdev. We're trying to see, that's why I marked it in a different color, we are trying to see if we can push the address handle information in some other means and reuse the netdev standard XMIT call. Okay. So, as I've said, IPOIB ULP initialization flow would be to allocate the RDMA netdev. This way, it can verify if indeed the underlying IB device supports such enhancement. If it's not, it can revert to the legacy code and the data path over kernel verbs. So this way, we fully backward compatible. And if the RDMA device was there, we can extract from the RDMA net device the actual net device and the net device private data. So the net device is being returned. In the private data of the net device, which is mentioned here, we have the RDMA net device. It has another pointer for IPOIB ULP specific private data and also the extra callbacks that are needed to allow control path dependent driver data. After getting the RDMA device, the ULP can update NDOs or change parameters in the returned net device, and only then calls the register, the Linux kernel register net device and register its net device towards the stack. In this slide, we show which event handling are being done in the ULP and which in the driver. So interface up, down, physical port up, down, the link state, the re-registration towards the subnet manager, PKey change. PKey change is the updating of the partition table of the NIC, similar a bit to VLANs in Ethernet, MTU change by the SM, and transmit timeout. All of these are is an existing code that is there in the ULP, and we would like to reuse that also in enhanced mode since it's not data path critical code. And what is data path is the send, the select queue, and the TX queue management, and also the receive in polling and receive queue management. All of that we would like to have in the driver. Okay, showing some initial performance. Very initial performance since this is pretty new. So with the standard IB/IB, we could see that with 100 gigabit per second max link speed, we could cap at 36 gigabit per second, and we basically saw that the CPU was 100% bound. and with the I/O traffic. And with the accelerated IP over IP bandwidth, we could reach the link rate with just 4 streams, 4 cores, 4 streams. So we've seen a nice scalability with the numbers of cores. Of course, we'll have more detailed performance once this matures. OK, so to summarize, the proposal here is basically use a single extensions to the kernel verbs IB device, which can allocate the RDMA net device. We reuse the net device as the carrier of the vendor-specific callbacks. So every update to the net device and new additions to the net device will be automatically added here, so the vendor that performs enhancement can also overload those functions as well. We keep the ULP code generic, so we allow backward compatibility with the vendors or providers that does not support the enhanced mode. And we allow optimized data paths, so we can have very optimized functions and hardware-specific optimizations for the data path. Any questions?
Thank you. Sorry.
I have one question about the performance, the standard. The standard IP over IP before you added the enhancements. That's is that the UD or the connected mode?
UD.
Okay, so
we compare to the UD because
because you have an enhanced UD now and the regular UD. Okay.
Yeah, as I've said, with the RC mode, we see scalability issues because it opens a connection.
No, I understand. But you could, but with the RC, you could probably get the 100 gig with just. With the old one, right?
I'm not so sure because there is still overhead with RC. There's no checksum offload, so there's no RSS, so you can't scale. I'm not so sure we'll get to 100, but we can test.